So, ladies and gentlemen, we can continue in our afternoon program before the coffee break. We've got last lecture to go through, and it will be the lecture by Andreas Čap, and you can see the very useful, usual triple of letters in our community, BGG, which goes back to Bernstein, Gelfand, and Gelfand. And I think this is, again, very much in the realm of what Ivan was always after. So he was excited by the opportunity to use algebraic tools to see complete classifications of operators which were invariant. Invariant, in his case, invariant with respect to the whole diffeomorphism group. And then a big group or growing group of people just was actually continuing in these steps, and we were interested in what happens if you have much smaller groups of automorphisms. You seek for the invariance with respect to them, and at the same time the group is still big enough to have only few of them. So Romanian geometry is not the right place, because there anything you can build from covariant derivative of this unique connection is invariant, right? But there are others, and there are BGGs, but Andy will actually perhaps provide a very unusual lecture, because it will be this time not shape analysis, but another kind of analysis, very practical one he will be heading at, right? So please, the floor is yours.
Okay. So thank you very much. It's a great pleasure to speak in the memorial session for Ivan Kolář. Actually he had quite a lot of influence on my development, starting from the fact that I was writing my diploma thesis based on a joint paper by Ivan Kolář and Peter Michor. So this was the basis for my diploma thesis. And all these things you have heard about before, like the emerging Central European seminar and the Kolář-Michor Slovak book, this all took place while I was studying. So I started in 85, and I wrote my diploma thesis in 89. And so this was also about the time where I first joined the Central European seminar and met Ivan Kolář. And I don't know, I mean, we didn't have that much personal interaction, but definitely this whole approach of naturality and the quest for naturality has been very influential for me and for the mathematics I did. All right, as Jan said, so for my talk today, the topic will maybe be a bit unusual because there's applied mathematics in the title, but rest assured that there will be much more BGGs than applied mathematics in the talk, so no need to be frightened. Okay, so let me explain a bit. So actually what I'm talking about is joint work with Kai-Bo Hu, who's currently in Oxford, and the first part of this has been finished already. The rest is in preparation. And the story here is the following. So I'll say more about that, but there is a Riemannian deformation sequence for general Riemannian manifolds, and in the case of a flat Riemannian metric, this is a differential complex. So in particular, you can apply this for a bounded domain in R3, and then this differential complex actually is very well known in a large applied mathematics community as either the Calabi complex or more descriptionally the fundamental complex of linear elasticity. And actually this fundamental complex or this deformation complex can be constructed in an algebraic or geometric way. Surprisingly, this is not based on Riemannian geometry, but on projective geometry, because it just depends on the projective structure underlying the Riemannian metric. And this came up, or the relation between these topics came up about 15 years ago, and some people in the room have been at a workshop at the IMA at this time, and there applied mathematicians got together with people working on these things, and this actually triggered quite substantial progress in the applied mathematics community, in particular towards finite element methods that can be used for linear elasticity theory and things like that. Right, and then, I mean, I didn't really notice that this continued in the applied mathematics community, but it did, and it was actually quite an active topic. And they just had this single example of a BGG complex and tried to generalize from this simple and maybe not so illuminating example. And and I got aware of the topic again only something like 3 or 4 years ago, when Kai-Bo Hu, who at that time was a postdoc under the direction of Douglas Arnold, contacted me and asked me whether there would be the opportunity that I tell him a bit about the general BGG construction, because they have some ideas and so on and so forth. And this started our conversation. And as usual in such things, it took quite some time to find a common language. But once the common language was found, it worked out quite well. And so we are interested in analogs of this, or versions of the BGG constructions that can be applied in numerical analysis or as the basis for finite element methods. And what one has to do there is one needs the complexes not for smooth sections or smooth forms, but for forms with low regularity, that is for Sobolev forms. And this is actually what I'm going to do in the talk, is I will outline how the construction of BGG sequences can be done using geometry and representation theory in the setting of this Sobolev regularity. The other nice side of this is that it provides a very simple version of the BGG machinery, because this is entirely done in a Romanian setting. So there is no need to think about conformal or projective invariants. There is no need to think about filtrations and associated gradients. Everything splits into direct sums. Moreover, you start with a flat metric, which makes the construction even more simple and things like that. But I guess on the long run, the constructions will also be useful for Romanian geometry. And as it is usual with these BGG constructions, you need a certain algebraic background in the construction. And this background is quite unexpected from a geometric point of view. In particular, if you just look at Romanian geometry, you would not come to the idea that this is what you want to do. But from the parabolic point of view, it is pretty natural. And it can be derived just from finite dimensional representation theory. And once you have this background at hand, the rest of the procedure is completely universal and completely algorithmic. Yeah, there's nothing, yeah, just few computations, and I will outline how this works. Okay, so let me start by recalling what the Romanian deformation sequence is. So this is a sequence that starts with the killing operator on vector fields. And so the first operator, this just can be viewed as the infinitesimal action or the infinitesimal change of the metric under an infinitesimal diffeomorphism. So in the second step, you have these symmetric two tensors, and then you get the linearized curvature operator. And I've just written Cm for its target, because what this looks like depends on the dimension and so on and so forth. And then there comes some linearized Bianchi map and stuff like that. Okay, so that's what the Romanian deformation sequence looks like. And the basis for these considerations is that this can be obtained as a BGG sequence. And this BGG sequence is associated to the projective structure that is defined by the Levi-Civita connection. So this is just the equivalence class of all torsion-free connections that have the same geodesics as the Levi-Civita connection up to parametrization. And the BGG construction in this setting starts from a so-called twisted Durham complex. So what you need is a certain tractor bundle and a certain tractor connection. And then you can couple this connection to the exterior derivative. You get a twisted Durham sequence or complex. And then you get an algebraic construction that leads to this BGG sequence. And now, in the setting we are in, there's no need to know what tractor bundles are, what tractor connections are, because if you fix a connection in the projective class, which is done by the metric that you have, then this tractor bundle simply is isomorphic to the cotangent bundle plus its second exterior power. And this is not difficult to understand because, okay, so the cotangent bundle you can replace via the metric by the tangent bundle, and the killing operator is defined on vector fields. And the killing equation tells you that the covariant derivative is Q-symmetric, and so you can view these as possible values in a point of a solution of the killing operator. And then the BGG machinery somehow implements prolonging this equation to a linear connection on this bundle. Okay, so here we just have two natural bundles and a direct sum of two natural bundles. That's it. Okay? Right, and now if you start with any natural bundle for Riemannian geometry, which just means that you start with a representation of the orthogonal or special orthogonal group, so in the case of the cotangent bundle, this is just the dual of Rn, and in lambda 2, it's lambda 2 of Rn star. Then on this bundle, there is a Levi-Civita connection. This Levi-Civita connection can be coupled to the exterior derivative. And so you get an operation usually called the covariant exterior derivative on forms with values in any natural bundle for a Riemannian metric. And if you have ever seen a formula for a tractor connection, then you notice that one ingredient for a tractor connection is always the slot-wise covariant derivative. Yeah, so in a way, you can view this tractor connection or the covariant exterior derivative of the tractor connection as a deformation or a modification of this covariant exterior derivative with respect to the Levi-Civita connection. And so we can view these covariant exterior derivatives as a starting point for the construction. And now, of course, in the setting that is needed for the applications in applied mathematics, things simplify further because they are just interested in domains in Rn, indeed actually in R3, but then for a domain in Rn, you can trivialize any natural bundle by parallel sections. So you can actually identify this natural bundle, the total space, with U times W, and you can do this in such a way that you trivialize by parallel sections. And so then WU-valued forms just get identified with W-valued forms. Yeah? And the covariant exterior derivative just gets identified with the exterior derivative times the identity if you trivialize by parallel sections. Okay, and now this space here of omega k U tensor product with W, just these smooth functions from U to lambda k Rn star tensor W. Okay, and in particular, you don't need any technology here to pass to Sobolev spaces. Yeah? You just replace smooth functions with values in some finite dimensional vector space by Sobolev functions in the same vector space of whichever regularity you want. Okay? Right. And now my talk will be, of course, a mix of naive approach and knowing what happens in the BGG machinery, and I will switch between these 2 points of view. So, from the point of view from the naive point of view, it's not clear how you get to something like that, but this is exactly where we will get to with a bit of help from representation theory. So, what we take is a representation V, which is decomposed into components, Vi, any number of components basically. I just start with some ON representation. And then what you can do is, or one way how to view a simplified version of the BGG construction is as follows. Yeah, so just keep in mind, in the case before we had this tractor bundle, which was just T star M plus its second exterior power. So here this would be V0 plus V1. We take forms with values in this bundle. This just decomposes. And we take this covariant exterior derivative. And then what the BGG construction does here is, first of all, you modify this slotwise exterior derivative by some tensorial terms in such a way that you still get a complex and that this complex computes the same cohomology. Yeah, and this is something that happens entirely on its own in the BGG setting, because this is just basically what the tractor connection does for you. Yeah, but here you put it in by hand. Okay? And then, okay, so you add a tensorial term, which, and you still get a complex that computes the same cohomology. But now your tensorial term identifies parts of K forms with parts of K plus 1 forms. And under this identification, if you do things well, you can see that these things cannot contribute to cohomology. Yeah, because, okay. And so what then the actual BGG construction does is remove those parts of the sequence, or some parts of the sequence, for which you can see that they get identified by these tensorial forms. And so you can change your sequence, or in the language that we have here, pass to something like a sub-thing without changing the cohomology. Yeah, and that's the basic idea that we will follow. Okay, and now the formulation that we use in the article is in a rather abstract setting. So what we do is we start with bounded Hilbert complexes. They are denoted by spaces Zij and differentials Dij. Yeah, and you should always, J will indicate the row, so it indicates which VI we are in. Yeah, bad choice of notation, I'm sorry about that. And you have Hilbert complexes, each of the same lengths. And so you should view each of these complexes as a row, and there are several rows of such complexes. Okay? And then the construction is done in the two steps described above, and the ingredients for the two steps are slightly different. So for step 1, we need bounded operators, Kij, and I'll get a diagram on the next slide, so don't be afraid. So these Kij just move you up one row. Okay, they stay in the same column and move you up one row. And from these you construct bounded operators S just by D composed with K minus K composed with D. Okay? And here's the diagram for that. Yeah, so you see the rows are indexed by the J, so we have a derivative going from Cij to Ci minus 1j to Cij to Ci plus 1j. And same in the next row. The K's may be vertically from one row to the next. So if you're familiar with BGG, you will ask yourself what that should be, and I'll come to that. And then you take D composed with K minus K composed with D to define S. Okay, so S moves you up one row and right. So it moves up and right. Okay? And in the standard BGG construction, this will just be the Lie algebra homology differential. Okay, so it will be the Dale. This will play the main role here. Okay, and then there's only one. Yeah, we can specify this case arbitrarily, define S's in this way, and then there's one thing to verify, which is that K's commute with S's. That's the only. Yeah, you have to. In this case, it's difficult. You need a third row. Yeah, then you can come up with an S, go up with a K, or go up with a K, come up with an S. Yeah, sorry. Otherwise, the diagram would have gotten too big. Yeah, but that's the only thing that we have to verify. In particular, we have to verify nothing if there are just two rows. And recall that this is exactly what happens in the elasticity situation. And then you can imagine why it was complicated to generalize. Yeah, because the only thing you have to verify wasn't visible in the simple example. Okay, yeah, this is what you need. And if you use this, then you just compute half a line. Yeah, you find out that D composed with S is minus S composed with D. Yeah, this is just by heating the defining equation for S with D from the left and from the right and using D squared is 0. And then from this, a short computation shows that S squared is 0. So you really get something like a differential. Okay? Right, and then you can already come to the first. This already is enough to complete step 1 of the whole procedure. So you twist the operator by defining dv to be d minus s. So you add to your horizontal term something that goes up and over. Okay? And of course, this doesn't make sense anymore on the individual rows, but it makes sense on the sum of all rows. No problem about that. Yeah, and so this ds is minus sd plus s squared is 0 plus d squared is 0 exactly means that this defines a differential on the sum of all rows. What is not so obvious is that if you define f to be the exponential of k, and if you see that k moves you up one row, you immediately see that this exponential actually is a finite sum, so it's a polynomial and not a series, so it's automatically a bounded operator. And you find out that this defines a bounded isomorphism of complexes from this twisted complex to the direct sum of the rows. Okay, so if you understand the cohomology of the rows, you immediately know that this twisted derivative computes the same cohomology. All right, and that's the bit of part 1. Yeah, I mean, it's not visible here that it's tensorial or anything like that, but you will see this is what happens in the actual applications. Yeah, we have modified the differential without changing the cohomology. Okay? So, for step 2, we will not need the case anymore. And so we will only assume that we have given the s's in such a way that these two equations that we have here, ds is minus sd and s squared equals 0. Yeah, so then you are really in a setting that is there for the BGG construction as well. Yeah. Okay. Right. But there is one important additional assumption, and this makes things slightly tricky in this setting, because it will be very important to know that the ranges of these S operators are always closed. Yeah, and now this sounds extremely harmless if I say these are tensorial operators. Yeah, their ranges will be more or less automatically closed, but only if the Sobolev indices for the source and the target match. And otherwise there's no chance to have closed ranges. And this will lead to some subtleties. Okay, so we always assume that the range is a closed subspace, and then by construction, of course, the range of any of the S's lies in the kernel of the next because they form a differential. Okay, and this is all assumptions that we need for step 2. And yeah, maybe if you look at this, and if you look at, let's go back to the picture up there, if you look at the total degree that is around here, so it's just I plus j on Zij, then you see that D raises the total degree and S preserves it. And that's the crucial step for the whole construction, is that if S is really tensorial, then this tells you that you get a lowest homogeneous component that is tensorial, and you can trade this off for differential components in higher homogeneity, and this is why the construction works. Okay? So this is briefly described here. So if you go to this total degree, yeah, I said all that. And this is exactly also the basis that you can see that, so assume that you have an element here, and there is a 0 above it, yeah, or there are all zeros above it. Then if this should be closed for dv, it must in particular be in the kernel of S, because that's the only thing that happens at this stage. So whatever is not in the kernel of S can be ignored here without changing the cohomology. This is the basic idea. Okay, and then the actual construction, I mean, this will be a bit difficult if you've never seen the BGG construction. It's hard to understand what is going on, so just view this as a funny sketch of how things work. So this S restricts to a bounded linear isomorphism from the orthocomplement of the kernel to the image. So we get bounded inverses and we denote them by T. So these are the replacements of del stars in the BGG construction. And we have a big simplification because T composed with S is not the constant Laplacian, it's just the identity. Yeah, so things get simpler. Okay? And then I take replacements for the cohomology or homology spaces. So I just take the kernel of S, of each of the S operators, intersected with the orthocomplement of the range of the previous operator. Yeah, this is a representative for the homology. Okay, and then you have things that you know if you have seen them in BGG. So if you look at the composition of T with D, yeah, so T was S inverse, so DT, yeah, you get one row down. And there are just finitely many rows, so this will be nilpotent. So you can write out something like a Neumann series to form inverses and stuff like that. So you get a simple explicit operator for somebody called G, and then you get a simple explicit form for somebody called A. So this is just the identity, sorry, it's not ID, it's the identity minus G composed with dV. And this will be the splitting operator, and then you get a formula for the BGG operator by just you apply this splitting operator, apply dV, and then project to these homologies. Okay? Right. So this is all explicitly written out, and then you do rather simple computations. And what you find out is that the splitting operator has the properties that we know from the standard BGG construction. So first of all, if you apply this splitting operator A to some alpha, then you land in the orthocomplement of the range of S. This is just the kernel of del star. Yeah, this is the replacement for the kernel of del star. And, projecting back, you get alpha. So it's really a splitting operator. And it also satisfies the characterizing property of the splitting operator. Namely, if you apply dV to its value, you again land in the kernel of del star, or here in the range of S perp. Okay? And as usual, these two properties characterize A. Yeah, so remember, this was like there was a series here. Yeah, and in the cases that we're interested in, T will be tensorial, but you have a covariant exterior derivative. So each power here adds an order of differentiation. Yeah, so these operators can get complicated, but you always have the simple first order characterization that is here. Yeah, so you don't need the operators explicitly, it suffices to work with their characterization. All right, and now if you look at the defining equations and you recall that dV was a differential, you immediately find out that dV composed with A is A composed with D, and then composing with another D, you see that A composed with D composed with D is 0, and this easily implies that D composed with D is 0. So you see that these BGG type operators again form a complex. Yeah, so this is how we get our new complex. So this epsilon star D is a complex, and actually this equation here, dV composed with A is A composed with D, exactly tells us that A defines a complex map from this back to the complex defined by dV. And then you can go through the usual arguments with lowest homogeneous components and stuff like that. And what you prove is, under the assumptions that we have made, this chain map A induces an isomorphism in cohomology. So in particular, this complex epsilon D computes the same cohomology as the sum of all the rows of the original complex. Yeah, so if this is something that you understand well, you know what the cohomology of this epsilon star d is. Okay, right. So now I completely forget about this general approach because it was just assumptions, 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 consequences, consequences, consequences. So how to get examples? And the examples actually come from representation theory and Lie theory. And so what you get is you start from a Lie algebra grading. G is G minus 1 plus G0 plus G1, so such a Hermitian symmetric type grading, where, yeah, I didn't write this here, G is semi-simple, in such a way that ON, which governs Riemannian geometry, is contained in G0. That's the only issue that we need. And there are two important, and G minus 1 is Rn, and G1 is Rn star. This is automatic for these AHS gradings. And they are available in two important cases. You have a projective case where G is SLN plus 1, and you have a conformal case in which G is SON plus 1, 1. And now if you do that, I mean, maybe one could motivate, so what do you want to get for these tensorial changes? You want to add something to the Levi-Civita connection which doesn't destroy flatness. So if you recall how the curvature changes if you change a connection, there is a term in which you get d of the change, and then there is an algebraic curve, an algebraic contribution in which you get compositions of the change with itself somehow. So the obvious thing to get rid of the d terms is just use some natural maps. But natural maps just come from representation theory of ON, and they will be automatically parallel. And the natural idea to get rid of the composition terms is use differentials. And this is what's happening. Okay? So now you start with an irreducible representation V of G. Then you can decompose this in a natural way according to eigenvalues of the grading element in such a sum, which has the property that Gi acting on Vj is contained in Gi plus j. Yeah, so in this sum, G minus 1 moves you down, G1 moves you up, G0 preserves the levels. So in particular, each of these Vj's is ON invariant and therefore something that we can build a natural bundle from. Okay? But the whole representation of G is also a representation of G minus 1, which algebraically seen is rather boring. This is an abelian Lie algebra and you have a representation, so what? But the interesting thing is this gives rise to a Lie algebra cohomology differential, which is G0 equivariant. Yeah, and that's just the usual delta that I denote here, mapping K's exterior power of Rn star tensor V to K plus first exterior power of Rn star tensor V. But this has the property that it maps the Vi component to the Vi minus 1 component. Yeah, because basically, is it Vi minus 1 or Vi plus 1? Yeah, I'm not sure. Anyway, it works out right. And of course, it satisfies del composed with del is 0 because it's a Lie algebra cohomology differential. And now, you see if you have an open subset in Rn, then you can compose with delta and you get a map from I forms on U with values in Vj to I plus 1 forms on U with values in Vj minus 1. And since this is just composition by a linear map, everything extends to Sobolev spaces without any problems. And you also see, I mean, it extends provided that the regularity of the source is at least the regularity of the target. Okay. Yeah, now, there are these cases which do not occur in the standard BGG construction. Where do they come from? Yeah, in all examples that we looked at, you can find such case. So you can always write the S's as dk minus kd for operators k mapping omega I of u tensor Vj to omega I of u tensor Vj minus 1, so just going up one row. And where they come from is you can compute them just from changing frames from a D parallel frame to a dV parallel frame. Yeah, that's the way how you can compute this case. And I will give you an example afterwards. Okay? And now, if we assume that the domain we are interested in is, I should say these operators are not natural, so they are tensorial but not natural, and they typically involve things like multiplications by coordinate functions, which of course is slightly tricky for Sobolev purposes. Fortunately, elasticity people like to work with finite volumes, so if we take a bounded open subset in Rn, then these multiplication operators make sense in a Sobolev setting without problems because the coordinate functions are bounded and smooth. Okay, so they are well defined provided that the regularity of the source is the same as the regularity of the target, which means that in the row above we need at least the same regularity as in the row we are given. Okay, and now we can fix some Q in R, and we denote Sobolev spaces by HS. That's great. Yeah. Okay, HS for Sobolev index S. Then we have all the ingredients to do step 1 by taking, so starting in some Sobolev regularity, reducing the regularity by 1 whenever we go a column right, because we want to have an exterior derivative there, and otherwise having the same regularity in each rows. Okay? Yeah, the problem then is in this setting the operators S are bounded, no problem, because they go to something of lower regularity, but they won't have closed image, because they go to something of lower regularity. So they will always have just map onto a dense subspace. And at this point, a bit of explicit work is needed. Namely, at this point, you can verify that you can change the regularities slightly. So if you assume that U has Lipschitz boundary, then you can change the regularity without changing the cohomology. And this is based on existing results on Sobolev-de Rham complexes. And basically, this is one of the ideas of the whole story. People know pretty well how to deal with the de Rham complex, but they don't know well how to deal with these more general complexes. And the methods of constructing these BGG complexes from de Rham complexes help you to carry over results from Sobolev-de Rham to these BGG operators. So you can change the regularity here in such a way that the initial regularity gets lower by 1 whenever you go 1 row down. And this does not change the cohomology, and then the Ks are no more bounded, but we don't need them. The S's now are bounded with close image, so we can move on to step 2. Okay, and then you just do step 2, you come to a Sobolev BGG complex, and the spaces in this complex can be either obtained by applying Costant's theorem to compute Lie algebra cohomology, or you can say we just know what they are, or if you are in applied mathematics and don't want to use Costant's theorem and compute with highest weights, you can just compute this explicitly rather easily in at least in simple cases. Okay, and then you see that you can also read off the orders. They are exactly determined by how much you go down when you go to the next step. So this is, if you start on gamma epsilon ij, you can only go to epsilon I plus 1k with k bigger or equal to j, and the order is just k minus j plus 1. So if you stay in the same row, you have order 1. If you go down 1 row, you have order 2. If you go down 2 rows, you have order 3, and so on and so forth. Okay. Yeah, and then there are some nice applications. So again, these are known techniques that you get if you have such closed range results and stuff like that. You also get closed range results for the BGG operators. These can be applied to derive inequalities. Among them, a new two-dimensional analog of the conformal Korn inequality, which was not known before, it seems, in the applied mass community. And we can construct bounded Poincaré operators using the known results for Sobolev-de Rham complexes. Okay, so let me do an example, and this is like the simplest example that people in the applied math community were not able to do because it has more than 2 rows. Yeah, and this is just conformal standard tractors. Oops. Any objections? Yeah, I'm afraid so. Okay, so this is like conformal standard tractors, or in the applied math community, the conformal Hessian complex. So you just have V0 equals V2 is R, V1 is R3. So you just take a triple of 1 forms to denote V1 valued forms. And then you see the Ks are just given by multiplication by coordinate functions and summing up, respectively by taking a form, multiplying it by the coordinate functions and putting it into a slot. Yeah? So it's about the simplest thing that you can do. But if you now compute S to be dk minus kd, you get dxl wedged with phi and summed up. And you can see this is just an expression of the identity map in coordinates. Same thing there. S will be just dx1 wedge omega, dx2 wedge omega, dx3 wedge omega. Yeah, or if you want, it's the position wedged with omega or something like that. Okay? And now the only thing that you need to apply, that you need to verify in order to apply the machinery is verifying this commutativity, and you can see that this is not difficult. Okay, and then you see, if you want to see what the complex looks like, you just have to check what the pattern of tails look like. And so you see there will definitely be cohomology here. There is no chance to kill that. There will definitely be cohomology here. And then you can just see, I mean, this is irreducible, so this is either 0 and isomorphism, and it's not 0. And here you get the alternation, you get the inclusion of the trace part, so you get trace-free symmetric part here. This column basically is dual to that one, so you get trace-free symmetric here. This will be an isomorphism, and that's the end of the story. So you see that the homologies are just, you can read off the degrees, therefore you can read off the orders of the operators. And you see that the complex that you get looks as follows. You get Sobolev space HQ with real values, HQ minus 2 symmetric trace-free tensors, HQ minus 3 symmetric trace-free tensors, HQ minus 5 real valued with operators of order 2, 1, and 2. So you also see that the Sobolev indices that come out in the end exactly reflect the orders of the operators, and you can immediately see that the first operator is the trace-free part of the Hessian. And now if you know that U is bounded with Lipschitz boundary, then regardless of the Sobolev order, the cohomology of this complex will just be the tensor product of the de Rham cohomology of U with R5. Thanks a lot.
Thanks, Andy, for the talk, and we have space for quick questions, if any. Are there some comments? Well, it doesn't seem to be the case. Everybody eager to go for coffee. So, thank you again.